Hi everyone. In the first part of this video, we'll go through some examples of using the standard error formula, and then we'll look at a situation in which the formula can be shortened so that the calculations are a little bit simpler. Before we go into those examples, we'll review a couple of points about the standard error. The standard error is larger. In other words, the means of the possible samples are more spread out and less accurate overall, when either the sample size is smaller or the population standard deviation is larger, meaning there's more spread or dispersion between the individual people in the population that's being studied. What this is really saying is that when you use a sample mean to estimate a population mean, you're likely to make more error when either you're using a small sample or the population that you're sampling has high dispersion. In those two situations, the mean of your sample is likely to be further away from the mean of the population. The standard error is really just a value that measures how far the sample mean is likely to fall from the population mean. So this is our first example of using the standard error formula. It says example 3 right here, but this is actually example 1 for us in this video. In this example, we have a population of 50 people. The standard deviation of the 50 heights in this population is 4.5. In this example, we're imagining a person who's going around and calculating the mean height of every possible sample of 10 people that could be selected from this population. The person is then plugging all of those sample means into the standard deviation formula to get the standard error. Basically, this person is using the long method of finding the standard error. What we're going to do is we're going to find out what answer this person will get for the standard error after he or she is finished with his or her calculations. But we're not going to use the long method. We're going to use the standard error formula. And to use the standard error formula, we just need 3 pieces of information. We need to know the size of the population standard deviation, and the sample size. So the population size is 50 because the population has 50 people. The population standard deviation is 4.5. That's the standard deviation of all 50 heights in the population. And the sample size is 10 because we're dealing with all possible samples of 10 people. So let's take those 3 numbers and plug them into the standard error formula. So capital N is the population size, little n is the sample size, and sigma is the population standard deviation. Now that we have those 3 numbers, we can plug them into the standard error formula that we learned in the last lecture. So the population standard deviation, which is 4.5, goes right here. The sample size, which is the little n, goes right here. The population size, which is the big N, goes right here. And then the sample size goes right here. And then the population size goes right here. And the -1 is just a part of the formula that's always there. So let's go through all of the steps and get our answer. First, we have to subtract inside of the fraction. 50 minus 10 is 40, and 50 minus 1 is 49. Now we divide inside of the fraction. We divide 40 by 49. 40 divided by 49 is 0.82. Now we find the square root of 0.82. You could find that by just pressing the square root key on your calculator. The square root of 0.82 is 0.91. Now we need to find the square root of 10 right here. The square root of 10 is about 3.16. Now we need to divide the 2 numbers in this fraction. We need to divide 4.5 by 3.16. When you divide 4.5 by 3.16, you get 1.42. Now we just need to multiply. 1.42 times 0.91 is 1.3 if you round the answer. So that's the standard error. That's the answer to the question. Now let's look at another example. This is actually the same situation we looked at last time. A person is going around a population and calculating the mean height of every possible sample of 10 people that could be selected, and then the person is calculating the standard deviation of all of the sample means to get the standard error. Basically, this person is using the long method of finding the standard error. And we want to find out what answer this person is going to get for the standard error, but we're going to use the standard error formula. We're going to use the short way of finding the standard error. Once again, to use the standard error formula, we just need three pieces of information. We need the population size, the population standard deviation, and the sample size. This time, the population size is 100, and the population standard deviation is still 4.5, and the sample size is still 10 because this person is still calculating the means of all possible samples of 10 people. Actually, the only thing that's changed in this example is the population size. The other two numbers are still the same. So we can plug those three numbers into the standard error formula. The population size of 100, the sample size of 10, and the population standard deviation of 4.5. We can plug those three numbers into the formula, and then our answer comes out to 1.3. It pretty much comes out to the same answer that we had last time. I think the answer is a little bit different, but it just became the same after I rounded the answer. Now let's look at one more example. This is actually the same situation again, and the only thing that's changed is that the population size is now 200. The population now has 200 people. And just like before, this person is going around and calculating the mean height of every possible sample of 10 people that could be selected from the population, and the person is calculating the standard deviation of all of the sample means to get the standard error. The person is using the long method of finding the standard error. And just like in the other two examples, we're going to use the standard error formula to find out what this standard error equals. We're going to find out what answer this person will get after he or she is finished with all of the long calculations. So we just need to know our population size, our sample size, and our population standard deviation. Then we plug all three of those into this formula, and then we do the calculations the same way. This time, our answer comes out to 1.4, which is a little bit larger than what we had last time. So that's the answer to the question. The answer is 1.4. Now I want to discuss this last part of the standard error formula. It actually has a name. It's called the finite population correction. And it turns out that this part of the formula actually only has to be used when the population size and the sample size are close to each other. If the population size and sample size are far enough apart, this part of the formula can actually be dropped off, and this over here becomes the entire standard error formula. The general guideline is that if the population is at least 20 times larger than the sample size, then the finite population correction can be left off, and you can just use this as the standard error formula. This slide explains why the finite population correction, or the FPC, can be left off of the formula when the population is 20 times larger than the sample. As the sample size and population size get further apart, the FPC gets closer and closer to 1. And when the population is 20 times larger than the sample, the FPC is so close to 1 that it doesn't really affect the final answer, which means that the FPC can just be dropped off of the formula. When you multiply something by 1, it doesn't change the answer. So when the population is 20 times larger than the sample, the FPC is so close to 1 that you're basically multiplying this part of the formula by 1. And multiplying something by 1 doesn't change the answer. That's why the FPC can be left off when the population is 20 times larger than the sample. So if the population is at least 20 times larger than the sample, it's possible to get a roughly correct answer using a shortened version of the formula that doesn't include the FPC. So we're going to go through some examples in which the population is 20 times larger than the sample, and we're going to show how we can use this shortened formula and still get a roughly correct answer. Here's our first example. We have the same scenario that we've been looking at before, in which a person is calculating the mean height of every possible sample of 10 people. But in this example, the population is 20 times larger than the sample. The population has 200 people, and we're dealing with a sample size of 10. So what we're going to do is we're going to use both formulas, the formula that includes the FPC and the formula that doesn't include the FPC. We're going to see how they both give us about the same answer. So here's the shortened formula without the FPC, and here's the longer formula with the FPC. The shortened formula gives us an answer of 1.42 for the standard error, and the long formula with the FPC gives us an answer of 1.39. Technically, this answer is correct, but by using the shortened formula, we got an answer that was pretty close to correct. 1.42 was pretty close to 1.39. So this slide is demonstrating how you can use the shortened formula for the standard error and get a roughly correct answer when the population is 20 times larger than the sample. Now we'll look at an example in which the population is 100 times larger than the sample. This is the same scenario we've been looking at, except now the population has 1,000 people. We're going to use both formulas, and we'll still see that they give us about the same answer. So this time, the shortened formula gave us an answer of 1.42, and the longer formula gave us an answer of 1.41. So this time, the two answers are even closer together. That's because the population and sample sizes are even further apart. The further apart the population and sample sizes are, the more accurate of an answer you'll get with a shortened formula. So if the population is 100 times larger than the sample, you'll get a highly correct answer using the shortened formula. So overall, as the population size and sample size get further apart, the FPC gets closer and closer to 1. And if the population is at least 20 times larger than the sample, you can leave off the FPC and still get a fairly correct answer for the standard error using a shortened formula. The reason why you can leave off the FPC and still get a fairly correct answer is because when the population is 20 times larger than the sample, the FPC is pretty close to 1, and it doesn't affect the final answer by very much. Now we'll move on to doing some other types of problems. We'll go through some problems in which we calculate the probability of the sample mean coming out to a certain number. This is our first example. In this example, we have a population of 4 people, such as a family of 4 people, and these are the heights of the 4 people in the population. What we want to know is the probability of randomly selecting 2 people from this population and getting a sample with a sample mean below 57. There are actually 3 steps that we'll need to go through to answer this question, and we'll go through those 3 steps together. The first step is calculating the mean of every possible sample of 2 people. The next step is counting the number of sample means that are below 57, and the next step is dividing that number from step 2 by the total number of sample means. So let's go through those steps together. This is step 1. In the last video, I showed you how to sort a population of 4 people into all possible samples of 2 people. You just have to pair person 1 with person 2, pair person 1 with person 3, pair person 1 with person 4, pair person 2 with person 3, pair person 2 with person 4, and pair person 3 with person 4. And that gives you the 6 possible samples of 2 people. Now that we have all 6 possible samples of 2 people on the screen, we need to calculate the mean of each possible sample of 2 people. We can find the mean of each possible sample by just adding the 2 numbers in each sample and dividing the total by 2. I already did that work for us, so right here we're looking at the means of all 6 possible samples of 2 people. Now that we have all of those sample means already calculated, we can move on to step 2. Step 2 is counting the number of sample means that are below 57. 55 is below 57, and 56 is below 57. So it looks like 2 out of 6 possible samples have a sample mean that's below 57. Now that we've counted the number of sample means that are below 57, we can move on to step 3. In step 3, we just divide the number of sample means that are below 57, which is 2, by the total number of sample means, which is 6. Two divided by 6 equals 0.3. So the probability of us randomly selecting a sample of 2 people from this population and getting a sample mean below 57 is 0.3. If we wanted to, we could leave the answer as a fraction, and the answer would be 1/3. So the probability of randomly selecting a sample of 2 people from this population and getting a sample mean below 57 is 1/3 if you leave the answer as a fraction. That makes sense because, after all, 1/3 of the possible samples of 2 people have a sample mean that's below 57. If 1/3 of the possible samples of 2 people have a sample mean below 57, then the probability of getting a sample of 2 people with a sample mean below 57 is just 1/3. So here's a graph of the sampling distribution. This is just showing the means of the 6 possible samples of 2 people. And this is just showing that 1/3 of the possible samples of 2 people have a sample mean below 57. That's why the probability of randomly selecting a sample of 2 people from the population and getting a sample mean below 57 is a 1/3 probability. Here's another example. In this example, we still have a population of 4 people, and these are the heights of the 4 people in the population. What we want to know this time is the probability of randomly selecting 2 people from the population and getting a sample mean between 56 and 57. This question has the same 3 steps that we did last time. So we just need to calculate the mean of every possible sample of 2 people. Then we need to count the number of sample means that are between 56 and 57, because that's what the question is asking. And then we need to just divide the number that we got from step 2 by the total number of sample means. So step 1 is going to be the same as it was last time. We're just sorting the population into all possible samples of 2 people, and we're calculating the mean of each possible sample. Once we get all 6 sample means, we're finished with step 1. In step 2, we need to count the number of sample means between 56 and 58, because that's what the question is asking about. We can see that 4 out of 6 possible samples have a sample mean between 56 and 58, if 56 and 58 are included. So we have the answer for step 2. We know that 4 out of 6 possible samples have a sample mean between these 2 numbers. Now we can move on to step 3. In step 3, we just divide 4 by the total number of sample means, which is 6. And our answer comes out to 0.67. When you divide 4 by 6, you get 0.67. And as a fraction, our answer is 2/3. And that makes sense because 2/3 of the possible samples have a sample mean between 56 and 58. In this graph, we can see that 2/3 of the possible samples have a sample mean between 56 and 58. That's why the probability of randomly selecting 2 people from the population and getting a sample with a sample mean between 56 and 58 is a 2/3 probability. Let's move on to our next example. In this example, we have the same population of 4 people with the same 4 heights. This time we want to know the probability of randomly selecting 2 people from the population and getting a sample mean above 57. We can follow the same 3 steps to get the answer to this question. In step 1, we just calculate the mean of every possible sample of 2 people, like we've been doing. In step 2, we count the number of sample means that are above 57, because that's what the question is asking about. And in step 3, we divide the answer from step 2 by the total number of sample means. We've already finished step 1. Step 1 is the same as it was before. We just sort the population into all possible samples of 2 people, and then calculate the mean of each possible sample. And then we get these 6 sample means. Once we have those 6 sample means, we just count the number of sample means that are above 57. These 2 sample means are both above 57, so it looks like 2 out of 6 samples have a sample mean above 57. In step 3, we just divide the number that we got from step 2, which is 2 samples, by the total number of samples, which is 6. When we divide 2 by 6, we get 0.33. So the answer to this question is 0.33, or as a fraction, the answer is 1/3. In this graph, we can see that 1/3 of the possible samples have a sample mean that's above 57. That's why if you randomly select a sample of 2 people from the population, the probability of getting a sample with a sample mean above 57 is 1/3. Here's another example. In this example, we have the same population of 4 people with the same 4 heights. And in this question, we want to find the probability of randomly selecting 3 people from the population and getting a sample mean below 56.67. So we're going to follow the same 3 steps to get the answer, but step 1 is going to be different because now we're selecting a sample of 3 people, which means that in step 1, we need to calculate the means of all possible samples of 3 people. So we're going to follow these steps to get the answer. We're going to calculate the mean of each possible sample of 3 people. We're going to calculate the number of sample means below 56.67, because that's what the question is asking for. And then we're going to divide the answer from step 2 by the total number of sample means. So in step 1, we sort out the population into all possible samples of 3 people. To do this, you just leave out one person each time. So sample 1 leaves out person 4, sample 2 leaves out person 3, sample 3 leaves out person 2, and sample 4 leaves out person 1. And these are the 4 possible samples of 3 people. Next, we can just calculate the mean of each possible sample of 3 people. To do that, we just add the 3 numbers and divide the total by 3, and we do that for all 4 samples. Once we get all 4 of the sample means, we can move on to the next step, step 2. In step 2, we just count the number of sample means that are below 56.67. Since this sample mean right here is 56.67, and the other 2 sample means are above that number, this is the only sample mean that's actually below 56.67. So in step 2, we found out that 1 out of 4 possible samples have a sample mean below this number right here. Now we're ready to move on to step 3. In step 3, we just divide 1 by the total number of possible samples, which is 4, and 1 divided by 4 is 0.25. So our answer is 0.25, or as a fraction, it's 1/4. In this graph, we can see the means of the 4 possible samples of 3 people that could be selected from the population. 1/4 of those possible samples have a sample mean that's below 56.67. That's why the probability of randomly selecting 3 people from the population and getting a sample mean below 56.67 is a 1/4 probability. Now we'll move on to talk about the z-score of a sample mean. Just like how every person in the population has a z-score that shows how far that person falls from the mean of the population, each sample mean in the sampling distribution has a z-score that shows how far that sample mean falls from the population mean. We talked about how the z-score of an individual person shows the number of standard deviations that that person falls from the population mean. In this case, the z-score of a sample mean shows the number of standard errors that that sample mean falls from the population mean. And this is the formula for the z-score of a sample mean. It's a little bit different than the formula for the z-score of an individual person, but it's actually pretty similar. The formula for the z-score of a sample mean says to subtract the sample mean by the population mean and divide by the standard error. This is similar to the other formula for an individual person, which says to subtract the person's value by the population mean and then divide by the standard deviation of the population. So these are the 3 parts of the formula: the sample mean, the population mean, and the standard error. I wanted to make a few points about the z-score of a sample mean. I want to show you how the z-score of a sample mean really works the same way as the z-score of an individual person. First, a sample mean that's below the population mean will have a negative z-score. A sample mean that's equal to the population mean will have a z-score of 0. And a sample mean that's above the population mean will have a positive z-score. Also, a sample mean that's far below the population mean will have a z-score far below 0. And a sample mean that's far above the population mean will have a z-score far above 0. So, a sample mean that highly underestimates the population mean will have a z-score that's far below 0, and a sample mean that highly overestimates the population mean will have a z-score far above 0. Overall, a z-score shows how extreme a sample mean is. If a sample mean is far below or far above the population mean, then that sample mean will either have a big negative z-score or a big positive z-score. Let's take a look at the z-score formula one more time. I told you that this was the z-score formula right here, the sample mean minus the population mean divided by the standard error. We know that if the population is 20 times larger than the sample, then the standard error formula is just this short formula right here. It doesn't have that FPC at the end. So if the population is 20 times larger than the sample, then this is the formula for the z-score of the sample mean. Let's use this formula to calculate the z-score of a sample mean. So we know that IQ scores in the general population have a mean of 100 and a standard deviation of 15. What this question is asking is that if a sample of 50 people is selected from the general population and the mean IQ of the sample turns out to be 107, what is the z-score of the sample? To answer this question, we have to turn the sample mean of 107 into a z-score. We can do that using the z-score formula. We just have to subtract the sample mean of 107 by the population mean of 100, and then put the standard error on the bottom. The standard error is just the population standard deviation of 15 divided by our sample size of 100. Our sample size of 50. Let's go through the steps to find the z-score. This is just subtracting on top. We subtract 107 by 100, and we get 7 on the top. That's our first step. Next, we can find the square root of 50. We can just enter 50 into the calculator and get the square root. The square root of 50 is 7.07. Next, we can divide on the bottom of the fraction. We can divide 15 by 7.07. When we divide those two numbers, we get 2.12 on the bottom. So far, we've subtracted on the top, then we found the square root of 50, and it came out to this number. Then we divided 15 by this number, and we got 12.12. We just have one more step. We have to divide 7 by 12.12, and then we get our z-score. So this sample of 50 people has a z-score of 3.13. A z-score of 3.3. To get the z-score, we subtracted the sample mean by the population mean, and we got 7. Then we found the square root of 50, and it came out to 7.07. Then we divided 15 by 7.07 and got 2.12. Then we divided 7 by 2.12, and we got the z-score. And it makes sense that this z-score came out to a positive number because the sample mean is above the population mean. Now we'll move into some questions in which we actually use the z-score of a sample to find the probability of getting a certain sample mean. If a sampling distribution follows a normal distribution, meaning it has a normal curve, or at least a roughly normal curve, then it's possible to use the z-score of a sample to find the probability of getting a sample mean lower than a certain number, the probability of getting a sample mean higher than a certain number, or the probability of getting a sample mean between two certain numbers. We'll go through an example of each type of question. And before we go through these questions, I want to mention that it's only possible to find these probabilities when the sampling distribution is normal. And the sampling distribution is normal, or at least roughly normal, in 3 situations. Those 3 situations are taking a large sample from a skewed population, taking a large sample from a normal population, or taking a small sample from a normal population. In those 3 situations, it's possible to calculate these 3 types of probabilities that I'm showing you here. If you're taking a small sample from a skewed population, then the sampling distribution actually isn't normal. The sampling distribution is skewed, and in that situation, it's not possible to calculate these types of probabilities. So let's look over the steps that are needed to use a z-score to find the probability of getting a sample mean below a certain number. There's actually only 2 steps that you need to follow. First, you need to calculate the z-score of the sample, which I showed you how to do earlier. And then you go to a table called the z-table, and you look up the z-score in the z-table. Once you look up the z-score, you get the answer that you're looking for. You get the probability. If you want to use the z-score to find the probability of getting a sample mean above a certain number, you actually have to go through 3 steps, and I'll show you what those 3 steps are. First, you have to calculate the z-score of the sample. Then you go to the z-table, And then you actually have to go to a third step. You have to get the decimal from the z-table and then subtract 1 by that decimal. And then that actually gives you the probability that you're looking for. Now let's look over the steps that are needed to use the z-score to find the probability of getting a sample mean between two specific numbers. First, you calculate the z-scores of both numbers that you're interested in. Then you look up both z-scores in the z-table, and then you subtract the larger decimal by the smaller decimal. And I'll go through a few examples of these types of problems with you. This is our first example. This question says that the heights of people in a certain population follow a normal distribution, and the mean height of the population is 60 inches, and the standard deviation of the population is 3 inches. This question says that a random sample of 9 people is selected from this population, and the heights of the 9 people are recorded. And we're going to use this information to calculate some probabilities. Before we can use z-scores to find probabilities, we have to find out if the sampling distribution is normal. So let's look back at the question to see if we can find out if the sampling distribution is normal. This question says that the heights of the people in the population follow a normal distribution, which means that the individuals in the population have a normal distribution. We know that if the population is normal, the sampling distribution is always normal, no matter what sample size is being used. So the answer to this question is yes, the sampling distribution is normal because the population is normal. So we know that the means of the possible samples of 9 people follow a normal distribution. Now that we know that the sampling distribution is normal, we can go ahead and use z-scores to calculate probabilities. This first question says, what's the probability that the sample mean will come out to a number below 57? Since this is a below question, we can follow the 2 steps that I showed you earlier. We just calculate the z-score of the sample, and then we go to the z-table and look up the z-score. So to calculate the z-score of the sample, we just follow this formula right here. We subtract the sample mean, which is 57 in this case, by the population mean of 60. In the question, I told you that the mean of the population is 60 inches. And we divide by the population standard deviation over the square root of the sample size. In the question, I told you that the population standard deviation is 3. So the population mean and the population standard deviation both came from the question. And I also told you that we were taking a sample of 9 people. So the sample size also came from the question. So what we need to do is we need to subtract on top, subtract 57 by 60, and it comes out to negative 3. Then we divide 3 by the square root of 9 on the bottom. First we need to find what the square root of 9 equals. The square root of 9 equals 3. So we're going to be dividing 3 by 3 on the bottom. 3 divided by 3 is 1. That's why we have 1 on the bottom. Now we just divide the top number by the bottom number. Negative 3 divided by 1 equals negative 3. So we finished step 1. We found our z-score. Now that we have our z-score, we can go to the z-table and find the answer to the question. I actually haven't shown you what a z-table looks like yet, but I created a little mini z-table on the slide. When you go to the z-table, you have to break up the z-score that you calculated into 2 separate parts. The negative 3.0 tells you what row to use, and then this last digit right here tells you what column to use. And then you just look at where the row and column meet up with each other, and then you get your answer. So this number right here is the probability of us getting a sample mean below 57. We finished the question. Now this question is actually an extension of the last question. It just says, what percentage of the possible samples of 9 people that we could select would have a sample mean below 57? To answer that question, all we have to do is just take the probability that we found in the last question and multiply it by 100. When you multiply by 100, you change the probability to a percentage. So what we've just found out is that when we randomly select that sample of 9 people from the population, 0.13% of the possible samples would give us a sample mean way down here below 57. And since 0.13% of the possible samples are in this area, we have a 0.0013 probability of getting a sample mean in this area down here below 57. And you can see the shape of the normal curve outlining the sampling distribution. When you go to the z-table, you're actually using the shape of the normal distribution curve to get the probability. So this probability that we found here actually came from, or it's actually based on the shape of the normal distribution. Now let's answer this question right here. What's the probability of getting a sample mean above 61 inches? This question is asking, what's the probability that the sample of 9 people will end up having a sample mean above 61? Since this is an above question, it has 3 steps. First, we have to calculate the z-score of the sample, following these, using this formula right here. We just subtract the sample mean of 61 by the population mean, and we put the population standard deviation and the sample size on the bottom. The sample mean came from this question up here, because the question is asking about 61 inches. The other 3 numbers all came from the question at the beginning. I told you that the population mean is 60 inches, the population standard deviation is 3, and that we're taking a sample of 9 people. And if we go through all of these steps right here, we get the z-score of the sample. We have to subtract 61 by 60 on top, and we get 1. We find the square root of 9, and it comes out to 3. We divide 3 by 3 on the bottom, and it equals 1. And then 1 divided by 1 equals 1. Now that we have our z-score of 1, we can go to step 2, which is to look up the decimal in the z-table. And once again, we have to break up the z-score into 2 separate parts. The 1.0, this first part, tells us what row to use, and this final digit at the end tells us what column to use. Since this third digit right here is 0, we use this column right here. And then we get this decimal from the z-table, where the row and column meet up. Now that we finished step 2, we move on to step 3, because remember, if the question says above, you have to go on to step 3, which is subtract the decimal in the z-table from 1. So in step 3, we subtract 1 by the decimal we got from the z-table, and then we get our answer. So the probability that the sample of 9 people will end up having a sample mean above 61 is 0.1587. And if we want to change the probability to a percentage, we just multiply it by 100. So if we multiply our answer by 100, we get this percentage. And what that tells us is that when we randomly select that sample of 9 people from the population, 15.87% of the possible samples of 9 people would have a sample mean above 61 up here. So that means that the probability of our sample mean coming from this area is 0.1587. The probability and the percentage go along with each other.